What's going on, class? Welcome to another lecture. Here's what we're going to do today. Basically, we've been doing chapter 12 for the last few lectures. We showed you the method of superposition yesterday, but by and large, we've been showing how to derive equations for slope and deflection, primarily for our beams. And so what we're going to do here in this lecture, we're simply just going to go over a few more example problems. From chapter 12, give you some more practice. Because you have an exam coming up, and I want to make sure that you at least have your number or your pool of example problems, not just the ones we do in the lecture, but also the ones that you can go back and practice from your homework assignments. So what we have here first is 1292. Just to get right into it, let's go ahead and read what we have here, and it says that the W8 by 48. Remember and recall that this is what's going to give us how we're going to determine our E and our I, right? Based on what type of beam and the shape of the beam. 836 steel, which automatically tells us that we're going to be dealing with 29,000 KSI, right? That's something we can keep in mind for our class. And it is subject to the loading shown. Determine the displacement at its NA. That's what it's asking us to find. What type of displacement is happening at the NA? So using the method of superposition, it informs us that, gotta make sure I'm still recording. It informs us that VA is equal to the V at A as a result of loading case 1 plus the V at A as a result of loading case 2. What do these two different loading cases look like? Well, the first one that we can look at is obviously this concentrated force at the end. Cantilever. You can show that there is going to be obviously a deflection of that nature. We draw it in an exaggerated manner. Low case 1 is a result of this 1.2 kips. That's what we'll say is low case 1. Low case 2 is going to be this moment right here at the center. And I want you all to pay some close attention to this, because here's where perhaps if you saw this on an exam for the first time or on a test, you may get a little confused. So we're going to do a couple of things here just to make sure that everyone is following along. This is VA2. But remember here, right? Remember this. Right here is where the moment is being applied. Right here is where the moment 2 kips per feet is going to be applied. So when we look at the back, especially with the method of superposition, there's going to be a deflection here, and we'll call that V at C, right? Because that's C. We're going to say V at C as a result of loading 2, right? And then check this out. There's going to be, if we look at this point as the baseline, there's obviously going to be an additional deflection happening at the end. And here's what we need to understand. We're going to be able to determine that by looking at the angle here. And this deflection here is going to be equal to the angle at C, right? We want to keep this in mind, multiplied times the length of the distance between A and C. All right, so keep this in mind. This is the distance between A and C, LAC. And we're going to want to multiply the angle, the additional angle, the angle at C, times that length of AC to get the additional deflection, right, that's happening at this end. So VA, get this right, is really going to be equal to V sub A as a result to 1, and VA as a result of loading case 2 is actually going to be V sub C, the distance that it deflects here, plus the angle at C times the length of AC. All right, are we following along? Because this loading case is right here in the middle, we're not going to be able to use in Appendix C the equation that acts as if this is at the end. We're going to have to figure out what that is and then add an additional deflection that comes as a result. All right, so let's go to the back of appendix of our book in Appendix C. See what we're working with here. as we begin to solve this. Appendix C is right here. In our first case, we're looking at a concentrated load at the end of the deflection. So that one's pretty easy. Here we go right here. This looks very similar to our loading case 1, doesn't it? Loading case 1, 1.2 kips at the end. So what we want to say is our vertical deflection as a result of that is going to be PL cubed over 3 EI. All right, we got a negative sign there. That's just telling us that it's going down. So we're going to write this as P. And the L that we're dealing with is the entire L. So just to keep the differences distinguished, we're going to say LAB cubed over 3 EI. Now, the next part. Let's look at V sub C, right? What is going to be the deflection right here as a result of that moment? Why is that important? Because if you look at Appendix C, yep, we're already out of Appendix C. There is no circumstance or no case that they show us back here where a moment is being applied halfway through the cantilever beam. We just have the moment being applied here at the very end. So what we're going to do in this case is we're going to act like, for now, that the cantilever is from C to B, and we're going to write for VC this value right here, moment M L cubed over 2 EI. So V sub C is going to be written like this: M L cubed, I'm sorry, not L cubed, L squared. But which L? Well, we're pretending like this is at the end because that's how it's given to us in appendix. So we're going to say LBC squared over 2 EI. Next, in order to get the remaining or the additional deflections that's going to happen as you go further out, we're going to have to say the angle at C, the angle that is created by this moment, plus LAC. How do we know what the angle is? Well, we look back here as if there is an angle being applied right where the moment is, because there actually is. And so we're going to write it as M L over EI. The question is, what L would this be? Well, it's going to be the L, the distance from the fixed end to where the moment is applied. So that means that that portion is going to be written as M times LBC again over EI. But not only that, because we also have to multiply by LAC, we're going to say here LAC. And that, my friends, is our equation. Put the book down out of the way. All right, so this is our equation that we're working with. I hope that makes sense when you look at Appendix C. Go ahead and pause it and make sure you're putting the right thing. But ultimately, we know that the deflection is going to be going downward. It's going to be going downward. All right, so let's get this thing going right now and write it out, or plug in our numbers. So first off, we're going to say that P is 1.2 kips. 1.2. The length of LAB is 16 feet. 16 feet. Cubed over 2. I'm going to keep EI as EI for now, for the sake of space. Then we're going to say plus. What is our moment? A moment is 2 kips. So we're going to say 2. LBC is 8 feet squared. That's going to be over 2 EI. Then we're going to have M, which is 2. Now LBC is 8 feet and LAC is 8 feet. So we can really write this as 8 squared over EI. And now what we can do is actually we can combine all these values together, right? So we got kip foot here. This is feet cubed, kip feet. This is feet cubed. All right. So all this is basically, if you add it up, look at my calculator. It's all going to stay in feet cubed at the top because I did not convert anything to inches yet. So 1.2, and then we have our denominators, right? When you get a common denominator, the value you should have here when you add this together is, let's go here, 16, 3, 8.4. Still keeping EI as is, plus 64 over EI, because I divided 2 into that, right? Plus 128 EI, right? And all these EIs are in kip foot cubed. We can combine these now. You all still can see, thank you. Yep, you can see when we add these together. Yep, 1830, 4 over, let's go ahead and plug in what E and I is, 29. That's KSI. And then I, for this beam, if you look in the back of the book or you look at your chart, that's going to be 184 inches to the 4. Right? And so since this is in kip feet cubed, let's go ahead and multiply this by 12 cubed to get it in inches consistent with that there. And when it's all said and done, what V at A, going downward, right, is going to be equal to is 593 inches. Take a moment, pause the video, make sure you get that answer so that we can see if we are on the same page. Cool? All right, review that. Let me bring it back into full frame for you. I'll let that chill for a second as I prep for the next one. Everybody good? All right, let's keep it moving. We're going to go to the next problem that we're going to work out for today. And that is problem 12-120. 12-120. Simple question. It's funny because these problems have simple like problem statements, but we know that they can get pretty involved and you really have to make sure you know how you're looking at it. All right, so off the bat, we see we're just going to find the reactions at the supports of A and B. We're going to recognize that EI is constant. And what's going to happen is because we don't have an actual number, our reactions are going to be in terms of W sub naught and L. So we're going to keep these, we're going to interact and use them as their numbers. We're also going to use EI, right? We're going to treat that as a constant as well, as it says in the problem statement. All right. Now let's go ahead and let's do this really quick. Let's recognize where there is a redundancy because this falls under the category of statically indeterminate. All right, statically indeterminate. And this is important to know because what you're going to see is that this is very similar to us doing, well, it's not very similar. It is the method of superposition, but we're going to take our redundant support, and we're going to treat it as if it is a different load case. So right here, we have a couple of reactions here, right? We have a Y. There's obviously a horizontal force, AX. And because this is fixed, right? Because this is fixed, there is also a reacting moment here, which we'll call MA. Now, that alone would be enough for us to be able to support this cantilever, right? Cantilevers are supported as a fixed end all the time. But we have over here a roller, which creates a redundant, right? A redundant vertical support here that we'll call BY. So what we're going to do now is still the method of superposition, but we're going to treat this BY as if it is an externally applied load, such that our two different load cases are like so. One is the result of this linearly distributed load. Boom, 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 right? I'm smudging my ink. All right. And then the other, and by the way, let me go ahead and draw that exaggerated displacement, right? That will be caused by that load, right? And we'll say, since it's B, we'll call that B sub B. Let's say B sub B prime. And then we're going to treat this second load case as if it's the result of a vertical force BY. Right? This is how we go about our statically indeterminate beams. And so the exaggerated deflection in this case, if BY was an externally applied load, would actually be vertical. We'll call that V sub B double prime. And so in order for this to be true, right, let's think about it as a literal case. This beam would be like this, right? Even though it has redundant members, redundant support, it still would be, not reflecting or not deflecting at the NB. It would be sitting right there on the roller. So even though we show this vertical placement, vertical force as if it would create a positive or upward displacement, and without it would create a downward displacement. In order for this to be true, literally true in real life or physically true, we're going to have to write this statement to be true. V sub B prime, the amount that it would displace with just a distributed load, is equal to V sub B double prime, the amount that it would displace if that redundant reaction was an externally applied load. So we have to equate those to each other. Another way we can write it is like this. V sub B prime minus V sub B double prime is equal to 0. All right. That is how we approach these statically indeterminate situations, still employing our method of superposition. All right. Let me see if I somehow can zoom out. To make sure we see as much as possible. All right. First things first. Is there any horizontal force that will cause us to have to really have a value, a deterministic value for the reaction AX? No, not at all. So we can just say that the sum of the forces in the X direction is equal to 0, which means that A sub X is equal to 0. There's our first reaction. You can basically solve that by intuition, right? Here's the next thing we can say. If we sum the forces in the Y direction, right? It seems like a very simple problem because they're talking about they're asking us to just determine the reactions. It's statically indeterminate. The hardest part is just making sure you understand how to look at it, how to use the method of superposition. We have AY going positively. What else do we have? We have BY going positively. And then we have a negative 1/2 base, which is W sub naught, times height, which is L. So 1/2 negative W sub naught L over 2. Right? And we can set that equal to 0. Next, let's sum the forces and sum the moments about A. Sum the moments about A. If this was the positive direction, we could say MA is one of those moments. Next, we would have this vertical force times wherever the resultant is, which would be 1/3 of L. So W naught times L over 2, multiplied by 1/3 of L, so L over 3. What else would be creating a moment about A? By would be, right? So we're going to say By plus a By force times the distance of L. Set that equals to 0. So now we have these two different equations. What are our unknowns? We don't know By, we don't know MA, and we don't know AY. So those are the three things we have to solve for. We only have two equations. Well, what do? We try to get another equation. Where is our other equation? This is our other equation right here. The fact that we said that the V sub B prime is equal to the V sub B double prime. So let's see what V sub B prime would be. V sub B prime will be found in Appendix C with a linearly distributed load there. What would that value be? Let's see. Well, we have it right here. W sub naught L to the 4th over 30 EI. So let's go and write that down. W sub naught L to the 4th over 30 EI. Boom. Next, what would it be if we set it equal to, and I'm gonna put this over here just so we can see it better, V sub B double prime, right? Because remember, they're equal to each other. So what is the V sub B double prime? This is gonna come from a By, right? A By going up. We're going to have to use this concentrated load here on the end, and the deflection would be the concentrated load P times L cubed over 3 EI, right? And this is when it's going down. The negative represents going down, but we know it's going to be going up. It's going to be going up. So what we need to write here is it said P, but we can go ahead and write it as By because that's what our force is. That's what our concentrated load is that we're using. By times L cubed over 3 EI. So these are equal to each other. This magnitude is equal to that magnitude. And the only unknown, because EI is a constant, we're treating W sub naught as if we know that value. L, we're treating as we know that value. This here, By, is what we would need to solve for. So if we were to isolate By, first of all, we can go ahead and cancel some things out here. EI on both sides, we can cancel that out. We can cancel out this L cubed with L to the 4th to get rid of, so that would just be 1 L there. Right? Another thing we could do is probably cancel out this 3 and reduce this 30 to 10 because we divide both sides by 3. We got 10 and that's 1. So there's a lot of algebra we can do right off the bat. And it's simply determine that By is equal to W sub naught times L over 10. Shall I catch that? Algebra did the rest of the work for us there. right? Because we know that these two magnitudes are equal to each other. We can set them equal to each other right off the bat, cancel out things that are redundant and things we can simplify. And we get our first reaction right here. Boom. So remember, we have these three equations right here. One equation, two equations, three equations to account for our three unknowns, AY, BY, MA. But now that we have BY, we can go and plug it into here, and we can plug it into here. In algebra, I'll just write what you'll get at the end of the day, would reveal that AY is equal to 2 W naught over L times over 5. If we do our first equation, and then M sub A, is equal to W sub naught L squared over 15. Now, again, very involved, but yet we still capture the solution for this statically indeterminate structure all on one sheet of paper. And it really came down to us being able to remember, or not even remember, because I'm just presenting to you for the first time, but for you to be able to recognize that in these cases, the goal is to remove a redundant reaction and use the method of superposition to write it as two separate load cases. So in this case, we had a cantilever beam. We looked at the displacement that would cause at B, V sub B prime, and we added it to a load case in which our redundant reaction is viewed, just simply viewed as a externally applied concentrated load that would also give us a vertical displacement of V sub B double prime. We set them equal to each other because we know that in actuality, there is no displacement at B. And then we use that as our additional equation down here, which allows us to solve for all of our unknowns. In this case, BY was solved for first. When we use that equation, we can plug it back in, got AY and MA as you see on the screen. So go ahead and give that a look, take a snapshot, screenshot, whatever you need to do as I prepare for, I think this will probably be our last example problem for this particular lecture. And then the rest is just practice, y'all. The rest is practice. All right, so what we're gonna do for our last and final problem is we're gonna look at problem 12-121. And I don't have a printout for it, but what we're gonna do is I'm gonna show you it on the screen right now. Switch my view. Here is the image. Here's the image, right? Pay attention to it. And the problem says here in the book, if I can just read it, it says the beam is used to support a 20 kip load, right? At the end, we see that. Determine the reaction that support, assume A is fixed and B is a roller. All right, so we got a very similar situation here where we're gonna have a fixed end right here, but it also tells us to assume that B is a roller. And then we're gonna try to solve for our reactions at A and B, knowing that this is another statically indeterminate situation. I'll keep this image up here in the corner for us as we move forward. So here's what we're looking at. Reposition that really quick. Boom, everybody see that? I'm mad like y'all can hear me in real time. All right, here we go. Let's sum the forces in the X direction first and foremost. Get that out of the way. That's equal to 0. Therefore, AX is equal to 0. I like to knock that out because yes, there is technically a reaction that affixes in horizontally, but because we have no horizontal forces, we're not going to get caught up into that. Let me go ahead and draw it though. It's what I definitely should have probably done first, but you all are with me. So here we have a vertical reaction, AY. We've already determined this AX to be 0, so we don't even need to draw it. But we also have a moment reaction. I'll draw this direction, M sub A. It told us to pretend like B is a roller. So that means that this roller is also creating a vertical force, By. Then there is a vertical concentrated force here of 20 kips. And another thing that we want to keep in mind here, right? We want to keep in mind that there is a length. There are two different lengths here. There's a length here. It's 8 feet. I'm going to write an L there right there because we're going to be looking again at Appendix C anyway. And Appendix C is going to give us, you know, what type of equation to use there. So we're going to call that L. And this here is 4 feet, which means that this distance compared to this distance is really just L over 2. L over 2, right? We know that's 8 feet. I'll just put it there just so you all won't get confused. And that's 4 feet. All right, but I'm writing it like that just so when we look in the back of our book or we look at Appendix C, we can go directly, our eyes can go directly to what we're looking for. All right, here it is. Summon the forces in the Y direction. Summon the forces in the Y direction. Well, to sum the forces in the Y direction, we have a Y, we have plus BY, and we have a negative 20 kips. So that equal to 0. Sum the moments about A. We have, if we keep our normal convention, the way that I drew MA would make this a negative MA. Right, negative MA. Then we have BY times, I'm going to say BY times L plus BY times L, keeping that there. And then we have a minus 20 kips. Yeah, that's going to be a minus 20 kips. And if we were to write the length, I'm going to keep L here. So if we were to write the length, it would be L plus L over 2. So basically 3L over 2. Or 1.5 L. All right, don't let that confuse you. In fact, it should help you when you're looking again at your equations in Appendix C. What would this look like in the method of superposition? That's the question. How we break this thing up? Well, moving forward, we know that we can look at the first loading case as a result of this concentrated load here. All right, I'll just write P there. It's 20 kips. But that's going to create a downward deflection of, well, it's going to be over here. If we need to know what is it asking us? It's asking us to get the deflection at A. Actually, we don't need to know the deflection at A. What we're really interested in is the deflection at B. So I'll say VB, right? Because we don't have even a letter for the end there. So yes, there will be a deflection there, but pay close attention to V at B. The other loading case, after having removed this redundant reaction and now placing it back, it would be something like this. Upward deflection. And BY is viewed. So this is VB prime. We'll call this VB double prime. You all remember what we do in our last example problem? Well, we know in order for this to be true, physically true, these two displacements are going to be equal to each other. So V prime, it's going to be equal to V sub B double prime. Right, so let's go ahead and write that equation out because we have this one equation, boom. We have this two equation, boom. We have these three unknowns. So our third equation is going to be like so. What is the displacement at V B prime according to Appendix C? Well, that is a concentrated load But the only example we have in Appendix C is where the concentrated load is at the end. However, in our problem, we want to know the displacement at BB, which is partially, not to the end, but it is in a location before you get to the end. So that means instead of looking at this equation of V max, which is at the end, we're going to look at this elastic curve, right? We're going to look at this elastic curve because ultimately we want to know the displacement V equals this here. We want to know the displacement at a certain distance along the length of the cantilever. So let's write it like this. We're using the elastic curve. We're going to say VB prime is equal to P X cubed over 6 EI times 3L minus X. That is what VB is going to be. But the thing is, since we have X's here, instead of putting X, we're going to put the actual length, right? So this here, X, will be L, because that's the distance along the length. And this X here will also be substituted for L. And then this L is talking about the length of the entire thing. Let's go back and look at it. This is what I just wrote here. And recognize that, make sure I focus it as much as I can. All right, cool. Recognize that what we have is an L, which in this example, L is the entire length of the cantilever, but X represents some point along the length of the cantilever. So that means that by the way that we drew our beam here, the entire length of the cantilever would be this L, which is 3L over 2. See why I wrote it that way? 3L over 2, because it's L plus L over 2. That's what the L is going to represent in the equation. And the X is going to represent this 8 feet here, which we labeled as L. So that's what the X's are going to be. So that's VB prime. Next, we're going to set that equal to V sub B double prime, right? This is actually where the load is applied, where that redundant force reaction is applied. So we can still use max in this case. We can use max in this case. So in this case, we're just going to simply write PL cubed over 3 EI, right? So let me pull that back. So what we'll write is, this is equal to P, as you just saw, L cubed over 3 EI. But in this case, L is actually L. L is actually L because according to, again, the demonstration of the example, it is showing this concentrated load at the end of the cantilever. So we're actually going to use L here, which is 8 feet. So that is L. All right, I hope this doesn't confuse you, right? We just have to know what they're referring to when they're looking at, when they're giving us these equations. And this is what I meant by the method of superposition isn't necessarily always a lot easier, because we see in this example, concentrated load at the very end of the cantilever, whatever length it is from the fixed end to the concentrated load is L. So in this case, because of how we labeled it as L, we're going to keep that L as L. But in this case, L really represents the full length, because it's the place to this concentrated load, which would be 3L over 2. All right, take a moment. If you have any questions, definitely reach out. Be happy to try to explain it to you in office hours. All right, so moving things forward, let's simplify this. Let's rewrite this before we get into solving mode. P, in this case, when it's for V sub B prime, P is 20. right? 20, and then X is L. L squared. In fact, let me keep it as P for now. I'm not going to do that. Let me just keep it as P. So P L squared over 6 EI times 3 times 3L over 2. So that's going to be 9L over 2 minus L is equal to P. And P in this case is actually BY. BY L cubed over 3 EI. And now we can use all this simplification. We can simplify here. We can, let's keep that as P. We can remove all our L's and we can solve for BY a little bit better in this case. So BY would be this. BY is equal to 7P over 4. 7P over 4. So this is, if you imagine this was a 2 over 2, that would be down to 7 over 2. L. You can distribute that through. Yep, 7P over 4. Now you can use this 7P over 4 to then plug into this equation here and into this equations 1 and 2. And what we will find is AY is equal to 3P over 4. And MA is equal to PL over 4. That's the equations. Now that we have P, though, we know P is 20 kips. And we know L is 8 kips. So we could go ahead and solve for these deterministically and find that AY is equal to 3 times 20. Yep. 60, 15 kips. BY 7 times 20. What is that? Divided by 4. $35 kips. And then MA 20 times 8. What about 4? 5 times 8. 40. 40 kip foot. Right? So I kept this problem kind of similar to the last one in that it was solved first. It was solved first as P's, right? I mean, search as equations, keeping the value as P, keeping the L as an L, realizing that ultimately we want to get these reactions, BY, the AY, the BY, and the MA. Once we got them in these terms, we can just simply plug in what P was, which is 20, and get these values down here. All right, take a moment, absorb that, take it all in. But with that being said, that will conclude today's lecture, problem 121. I hope that this has gotten a little clearer to you, particularly how you break things down in superposition, and then how you use algebra for the most part to get these reactions and solve for the problem. All right, all the best on your upcoming exam. Definitely reach out if you have any questions. I wish you all the best. Take care. Peace.